remember the formula for momentum. Momentum, which is vector quantity, is F multiplied by V. And the change in momentum is the impulse. And we have also the force is the rate of change of momentum, which is the time derivative of momentum. We have these three relations from the previous lecture. Now, we need to learn more about conservation of linear momentum. If we have two objects or two sources of forces, as you see, this is A and B. A and B. If we have force from A on B, so we have force from A on B. This force will act on the object B and will accelerate it. So this will be equal to dP by dt for the object B. If we have another force, as Newton's third law tell us, we have another force, action and reaction. This is F from A on B, and we have another force from B on A, which is the same force but with negative sign because the opposite direction. Now we have another force from B on A, which is equal to dP by dt, but now the force will act on the object A, and the change in momentum will be for the object A. Now, we know that F from A on B is equal to F from B on A, but with negative sign, right? Now we need to use the momentum representation for these forces. From that, we have d by dt for the first force, which is the momentum, the change in momentum on object B, because the first object A will apply a force on the other object B, it will move it, and vice versa, which is equal to minus dB A by dt. Now just I need to move this to the other side. It will be dP B by dt. The minus sign will be plus, which is equal to T dB A over dt. This will be equal to 0. Now I can take the time derivative outside. I have T E plus T A equal to 0. Now, if this is XY plane, but it is T and P plane. Now, what is the meaning that d by dt is equal to 0? How much the slope for this? If I throw x with y, what is the meaning by dy by dx is equal to 0. That means the slope is equal to 0. That means the function, we draw it here, is horizontal, and its slope is 0. And the same thing is for our relation here. If we have now the momentum P, which is equal to PA plus PB, and the time on the x-axis, then we have dP by dt equal to 0. That means the momentum relation is constant. If we see for example, let us pick a number here, which is 15, for example, 15 kilogram meter per second. At t equals 0, how much the momentum? It is 15. At t equal 1, it is 15. At t equal 2, it is 15, and so on. That means the momentum, if the derivative of a function is equal to 0, then the thing inside this derivative is constant. That means P A plus B B plus whatever we have inside here is equal to constant as vectors. Maybe we have more than one object. Okay, any time derivative or any derivative equal to 0 means that the functions inside the derivative is constant. Okay, by this we know that the momentum is conserved. We mean by conserved, it has constant value. After 1 second, 2 seconds, 3 seconds, and so on, we have the same magnitude of momentum. This momentum, because we are dealing with the velocity, this is a linear momentum, by the way. This is linear. I think we will deal with angular momentum later. Okay, what else? Any questions so far? Now, if we look at this system, this is a closed system. The forces between the objects in our system are, all of these forces are internal forces. So the forces are internal forces. We don't have any external force. We didn't apply any force from outside. Okay, there is no any external force. If we apply any external force, then we will find that the momentum will change. Okay. We will see by the examples. We have an experiment. This is the timeline. We have an experiment here. Maybe it is collagen. We will see that if the momentum conserved, that means that momentum before is equal to momentum after. So we need to differentiate between the period before the experiment and after the experiment. We will see that by doing some examples. I'm sorry, I'm still a little bit sick, so I am a little bit tired. Now we have example. We have a rifle with a bullet inside it. The mass of the rifle is equal to 3 kilograms. And its velocity before shooting is equal to 0. We have inside it we have a bullet inside it. The mass of the bullet is equal to 0.005 kilograms. Its velocity initially, v small, equal to 0. Okay. I'll name this M rifle, V rifle, M bullet, V bullet. Okay. What is the momentum? The total momentum now. You need to compute the total momentum. The total momentum is equal to momentum for the rifle plus momentum for the bullet, which is equal to, that's the relation for the momentum, which is M multiplied by V. M, right? Plus M for the bullet, V for the bullet. That's it. This is summation of P before is equal to the mass for the rifle is 3 kilograms and the velocity is 0 plus 0.005 multiplied by 0, which is equal to 0 kilograms meter per second. This is the total momentum before the shooting, because we have masses, but the velocities are 0. Okay, after shooting, we have a velocity for the bullet, 300, I think, meters per second in I direction. Yes. In I direction. I have. The directions are important in our solution. And by the way, if you you know that the rifle will handle velocity in opposite direction. We have V for this rifle after the shooting. It has the same mass, 3 kilograms. We need to compute this velocity. Okay. Now we know our system has total momentum initially is equal to 0. If you remember the computing of mechanical energy, the mechanical energy equal to kinetic energy plus the potential energy, and the mechanical energy is equal mechanical energy each time, right? And the momentum is also is conserved and equal the momentum each time. So the momentum after is equal to the momentum before, equal to 0. Okay, what is the momentum after? Is equal to the momentum of the rifle after plus the momentum of the bullet after, which is equal to the mass, capital mass, multiplied by the velocity of this rifle as a vector quantity, plus the mass of the bullet multiplied by its velocity after. I will not write after, but if we start our solution for the before stage, then we go to the after, then all the solution now for the after here, okay? Now, P after is equal to 0, is equal to 3, as we know that, the mass of the rifle. The velocity is unknown, plus the mass for the bullet is the same, multiplied by its new velocity after the shooting, which is 300 meter per second in positive I direction. Okay. Now we have a relation with just one unknown value, which is V. We can move this term to this side, it will be the negative side. So it will be minus 3 VR is equal to this multiplied by this, which is 1.5 meter per second in I direction, right? Now we have minus 3. We need to divide over minus 3 both sides. (1.5) over minus 3 meter per second I have, which is equal to minus 1/2 meter per second I have. The minus sign means we are moving in the opposite I direction. We can put the minus here also, which is equal to 1/2 meter per second in negative I direction. That means the rifle will move to this direction with velocity 1/2. But the velocity of the bullet is 300, too much higher than this velocity. And that is because the difference or the ratio between the masses, the bullet has small mass. So its velocity will be higher than this one because its mass is too much than this one. Because this is 3 kilograms and this is 5,000. If we need to compute the work done on both of them, if I need to compute the the kinetic energy for the rifle and the bullet. Good. The kinetic energy for the rifle is equal to half multiplied by m. This is the kinetic energy relation. Half multiplied by 3 multiplied by minus half square minus half square. This will be equal to okay. Let me compute now the kinetic energy for the bullet, which is equal to half multiplied by 0.5005 multiplied by the velocity, which is 300 squared. This will be equal to a value, and this will be equal to a value. If you remember that from before, this is equal to how much the kinetic energy before? Kinetic energy is equal to how much for both of them? 0. For both of them, 0 plus 0. Now we have a new kinetic energy. So we have a change in kinetic energy. Remember that we have the work is equal to the change in kinetic energy. Now we have two works. The first work is done on that rifle, which is equal to the change in kinetic energy, which is the kinetic energy, this one, minus 0. This is the work on the rifle. It will be small. And this is the work done by on the bullet. It will be huge. And you can see now. The ratio of the works done on the two objects are related to their masses. How can I tell you that? There are many additional resources in Canvas. You can look at them. There's videos, and you can understand more things more than me. If there is a person want to push a box, for example, we know that he can push it with a velocity, and he also will be pushed to backward with another velocity. If this box is small, then its velocity will be higher than that reaction force on the person. Then the work, it will gain the maximum value of the work because its mass is small with respect to the other object. That's what we see here. It is easier to move the bullet than move the rifle. And you can see also that when you see a shot from a cannon, the projectile go away with fast velocity and the cannon velocity backward, but not that high as the projectile from it. Okay. Any questions online? Offline? Another example. We have a collisions now. We will talk about collisions by detail, but we have an example now. Okay, we have two balls, A and B. The mass of A is equal to 0.5 kilograms, and its velocity V of A is equal to 2 meters per second in I direction. This is before the collision. So I will put 1, means before. The mass of the ball B is equal to 0.3 kilograms, and its velocity V initially before the collision is equal to 2 meters per second in negative I direction. Okay, then we have a collision. This is A and this is B. And they get going away from each other. This is B with B2 means after the collision. And this is A with velocity VA2 after the collision with the same masses. Now, if V2 is equal to 2 meter per second in I direction, what is the velocity for that ball number A? If you look here, the velocity initially for this one is 2. The velocity for this one is also 2. To this direction, to this direction. Maybe some of us look at this, you will see that the velocity for this is 2. Again, it is 2. Then this will be equal to 2. But we need to compute that. Maybe this wrong. This idea is wrong. So before we need to compute the momentum. Is equal to P for A before plus P for B also before, which is equal to MA V A 1 means before plus MB V for B 1 means before, and now we put the numerical values. MA is 0.5. V for A, it is 2. I have, right? We are talking about vectors. Plus the mass for B, it is 0.3. And its velocity is also 2, but with negative sign in I direction. This will be equal to, so P initially is equal to 0.4. This will be 1. This is minus 6. This is 1 I hat minus 0.6 I hat, which is equal to 0.4 I hat kilogram meter per second. Any questions? Any questions online? Now, this is the momentum before. We need to compute the momentum after. It is the same. Because it is the same, we can compute the velocity for this one. Okay. After we have total momentum after, which is 2, is equal to the momentum before, which is equal to 0.4 as a numerical value. Okay. Now 0. The total momentum after is equal to 0.4 in I direction is equal to the mass of A. Again, I will write it again, multiplied by VA later, after, which is 2, plus MB multiplied by the velocity for B, but later, after that collision. Okay, 0.4 in I direction is equal to the mass for the A is still half, multiplied by the velocity, which is unknown, VA2, which is after, plus the mass for this 0.3, multiplied by its velocity, which is 2 in I direction, in positive I direction. We don't have any negative sign. Now, I'll move this to there. This will be equal to 0.4 in I hat minus 0.6 I hat is equal to 0.5 VA again. This is negative 0.2 I hat is equal to 0.5 VA. .5, which is 0.5. Okay, from this VA later after the collision is equal to negative. I need to divide over half. This will be equal to 0.4 I hat with negative sign, kilogram meter per second. As you see, its velocity later, the ball A, it is not 2, it is 0.4. Because we have change in the direction and the velocity, and we have this mass is not the same like this mass. So when you see this question and you see 2, 2, and this is 2, and you have multiple choice, don't put 2 directly. Okay, so this velocity will be equal to 0.4 with negative sign because it is to the negative I direction. Yes, I direction. Any question? Online? Any question online?
I have a question.
Yeah.
So is saying negative 0.4 I, do you want us to say 0.4 in the negative I direction, or is it like the same thing? Or is negative 0.4 in the regular I direction fine?
Negative 0.4 in I direction or 0.4 in negative I direction. I can move the minus sign in the direction.
Okay, thank you.
Is that that's it? Okay. Now, yes, we have some important notes. Let me put this table here. Make more understanding. Oh. Okay. Okay, let us look now at the momentum, the first three columns. Ball number A has initial momentum 1 in I direction. And ball number 2 is equal, has momentum minus 0.6 in I direction. I will put the minus with the numerical value and all of our directions in I direction. Now, the momentum for the ball number A, which is 0.2, this one is 0.6. Now, ball A has momentum after is equal to its mass multiplied by velocity. The mass is 0.5 and the velocity is 0.4 in negative direction. We find that the velocity is 0.4. This will be equal to 0.2, yes, with the negative sign. Look, before the collision, this is the collision. Okay. Ball A has momentum equal to 1. Ball B has momentum equal to negative 0.6. After the collision, ball A has momentum negative 0.2. Ball B 0.6. What about the change in momentum for both of them? The change in momentum means P2 minus P1. So this minus is how much? We have negative 0.2 minus negative 0.2 minus 1. It will be equal to negative 1.2. What about this? 0.6 minus 0.6. This is minus sign. So this will be equal to 1.2 with positive. Now, the change in momentum for the first object is equal to the change of momentum for the second object with negative sign. What that means? We see that in the beginning of this lecture, that we have force from A on B is equal to minus force from B on A. And I'm asking now, is the ball A gain or lose momentum? From the negative sign, it is lose, right? The ball number B gain momentum. So the momentum from ball A gained by the ball B. So the momentum, is the momentum conserved or not? If we add the momentum before plus the momentum after, how much that result? If we add this to this, the change in momentum to the change in momentum, it will be 0. This means any change in momentum in any object, it will appear in the other one. So the momentum will stay conserved. This is about the momentum. Now we'll talk about the kinetic energy. We are familiar with kinetic energy. The momentum just M multiplied by V, which is a vector quantity. Now the kinetic energy mv squared. We need to see now kinetic energy before the collision and after the collision. This is an introductory to understand the elastic and inelastic collisions. Let me complete the table. Now this is the ball A and the ball B. This is the velocity before. This is the velocity after. This is the change in velocity. And this is the change in velocity multiplied by the mass. The velocity before for the ball number A is 2I. And this is minus 2. After, this is negative 4. This is minus 2. Sorry. This is negative 0.4. Right? This is at this velocity after the collision for ball number B is plus 2. What about the change in velocity? Minus 4, minus 2, it is minus 2.4. 2 minus 2, it is positive 4. There is no meaning. If we look at the change in momentum, we will see that the numerical values are the same with negative sign. But for the velocities, there are no meaning for the change in velocity. It will not be easy understood by this. But what if we multiply the change in velocity by the mass? The mass of this is 0.5 and the mass of this is 0.3. Okay, multiply but this by 0.5, it will be negative 1.2. Then this will be positive 1.2. The change in velocity multiplied by the mass, it is easy. It is the change in momentum. Because the momentum is equal to mass multiplied by the velocity. The change in momentum is equal to the change in mass and velocity, but the mass is constant. Then the mass come out from the delta sign, then it will be, this is delta sign, you know that? So delta V is equal to M delta V, which is this one. Now the change in velocity multiplied by the mass is the change in, it's the same. You can compute here the kinetic energy before and the kinetic energy after. Let us move now to this idea, which is the elastic and elastic collisions. Any questions on that? Momentum collisions. We have two types of collisions. As you see, we have elastic elastic collagens, and also we have inelastic. As we see from the previous example, the momentum is conserved always. So in elastic, we have the momentum is conserved. Means P, or the total momentum before the collagen is equal to the total momentum after the collagen. Is that understood? Also, this is the same for the inelastic. Here also, we have the momentum before the collagen is equal to the momentum after the collagen. It is conserved, both of them. But if we look at the energy, if you remember the example, we don't have any change in potential energy. We will not care about it. We care about the kinetic energy. So we'll talk about the conservation of energy or the kinetic energy. So the second point, the kinetic energy is conserved also. Means the total kinetic energy before does not a vector. The collagen is equal to the total kinetic energy after. The summation, maybe I have two objects, like ball number A and ball number B. I add the momentum for them or the kinetic energy for them. But in this case, for the inelastic, the kinetic energy is not conserved. The kinetic energy before is not equal to the kinetic energy after. There is a lost part of this energy. If we have collisions between two balls, you can hear the sound between for this interaction, right? This sound is a change of the energy. So the energy will be lost. Sometimes we have two clay balls. Okay? It's clay. When you make a collision between them, then they will stick together. They will be just a one mass, right? The shape of these objects is changed. Their deformation is changed. This take or spend some energy from our system. That this energy comes from the kinetic energy. Then the kinetic energy later, it will not be the same as the kinetic energy before. Maybe there is a heat when there is a collision between the two objects. Also, this is a waste of energy. In general, in the nature, all the collisions are inelastic. But we can assume that some of them are elastic, like glass balls or the atoms or any object in the lab. If we need to assume it as an elastic collagen, then we can assume it, and we can assume that the kinetic energy is conserved. But when we, for example, look at this collagen for two things, and their shape is changed, and also two soft objects when they are collide together, their shape is easy to be changed. Then this kinetic energy is not conserved before and after the collagen. Okay. We solved an example before the previous lecture. If you remember when we throw a ball and this ball deform its shape and reflect from a wall, this deformation of the shape makes the collagen inelastic. And we see that when we found that the velocity after the collagen is less than the velocity before the collagen. And we thought that maybe there's some heat and some scratching the wall and something like that. But this inelastic collagen, not totally inelastic, because the ball separates itself again and we can distinguish it from the second object, which is the wall. But for the two balls of clay, when they are sticking together, then they are totally be a new object with this is mass number 1, this is mass 2. Now this is mass number 1 plus mass 2. This collagen is totally inelastic collagen because we change all of the system. We have a new object now. Okay? Any question about that? Now for elastic, we have the momentum is on zero. The momentum before is equal to the momentum after. The momentum before, if we have two objects, M1 and M2 with velocities V1 and V2. The momentum before is P for the first object. Let us name it A again, and this is B. The momentum for A, B4 plus the momentum for B, B4 is equal as just we solve it. The momentum for A after plus the momentum for B after. What about the kinetic energy? Kinetic energy is the same. The total kinetic energy before is equal to the total kinetic energy after. Total kinetic energy before is kinetic energy for A before plus the kinetic energy for B before is equal to the kinetic energy for A after plus the kinetic energy for B after. From this, what is the momentum for this first object? It is MA VA1 plus MB VB1 is equal to MA VA2 plus MB VB2. This is the same equation what we used in the previous example. We have this new equation now for the kinetic energy. It is the kinetic energy for the first object. It is 1/2 MA VA1 squared. This is the kinetic energy relation, but for the object A and before the collision. Plus this is the kinetic energy for the first object before the interaction, and this is the kinetic energy for the second object before the collision, which is the interaction, which is equal to the kinetic energy later. This is for elastic. 1/2 MA VA later squared plus 1/2 MB VB later squared. If you look at this, we have distinguishable masses. MA is still MA before and after, and also from the kinetic energy relation. The mass for A and B are still the same, MA and B. But we will compute for the total inelastic, the mass will be changed. Now, because all the masses will be just one mass after the collision. Any question for that? Okay. Any question online? I will do this more. Now for totally inelastic. For inelastic collisions. For totally inelastic, we have the mass A and the mass B collide together. After the collision, we have all of them in one mass. This is A and this is B. This is mass A and this is mass B. And this is mass A plus the mass B. This is after. This is the mass what we will use after the collision. Now the momentum will stay the same. The momentum will be conserved. I will put it directly. P A before plus P D before is equal to the total momentum after. It is in general one mass. It is A plus B together, but this is after. If I put down here M A V A before the plus MB V B before is equal now to, we have one mass with one velocity. This mass, the total mass, is M1 or MA plus MB together, multiplied by the velocity for this total mass after. We can name it, if you like, AB. After. This is the first relation. The second relation for the kinetic energy will not be considered. The kinetic energy before kinetic energy before is equal to half MA VA squared plus 1/2 MB VB 1 squared. This is VA before the collision. The kinetic energy after. Kinetic energy after is equal to 1/2 MA plus MB multiplied by the velocity square. They are not equal together. We can compute this. We can compute those, but they are not equal together. We can compute also the wasted energy between the before and after this experiment. If you look at the conservation of momentum, this is the relation for the elastic collisions. The left-hand side is equal to the left-hand side. But after the collision, we have change between the elastic and inelastic. We have two separate objects. They are still A and B, but here they are just one object together. But the momentum is conserved. We have equal sign between them. The kinetic energy for elastic collisions is conserved. We have separate distinguishable A and B masses, but in the elastic collisions, the kinetic energy is not conserved. And you can compute that. We have an example, I think. Any question? How do you know the relations? Example, we have inelastic collision. We will use these relations. This and this. If we have a bullet, name it A. So MA is equal to 0 as the previous one. And the velocity of A before the collision is equal to 300 as before, meter per second in I direction. It will hit a box of wood. The mass of this box is equal to, make it more easy to compute later, 995,000 kilograms. And its velocity before is equal to 0. After the collision, the bullet will go inside the box and it will move. Okay. This is the way that used in the factories to measure the velocity of the bullets. They measure the velocity of the box after the collision, and they know by that, and they know the mass of the box and the mass of the bullet. They can know and compute the velocity of the bullet before the collision. But now we know the velocity of this bullet. After the collision, the bullet is inside the box, and now we have a new object. We don't have two objects. We have total mass is equal to the mass 0.005 plus 0.995, which is equal to 1 kilogram. It is easier to be computed now. Now, what is the velocity? V after. I name it here V pi. You can name it VAB after. We need to compute it. We don't care now with the elastic collision equations. We will use that one. Any question about this example? About the givens? Now, for the momentum, we are sure that the momentum before is equal to the momentum after as a vector quantity. The momentum before is MA VA before plus MB VB before, which is equal to the momentum after. It is the total mass multiplied by the velocity AB after. I put them all together in one equation. I will not compute that before, then compute that after. All together, you can do that. M1 is 0.005 multiplied by its velocity, which is 300, plus 0.995 multiplied by its velocity, which is 0. Now this will be equal to 1, which is the total mass multiplied by the velocity after. This term is 0 as we see. This term is 1.5. It's equal to 1 multiplied by that one. So the velocity for the two objects is 1.5 meters per second in x direction. The same x direction. If you imagine, you can imagine that the velocity of the bullet is 300 meters per second, means can pass from here to the end of the yard, I think, by a second. But after the collision, the velocity is just 1.5, means like this. 1 second. It will be because the energy of the bullet is spent. This. Any question online? Is this understood? Now, what about the kinetic energy? If we need to compute the kinetic energy before and after, and if we need to compare them, we use this. Now, kinetic energy before is equal to 1/2 MA VA squared plus 1/2 MB VB squared again, which is equal to 1/2. The mass is 0.005. The velocity 300 squared plus 1/2, 0.995 multiplied by the velocity, which is 0 for the box squared. This will be equal to 0. This will be equal to kinetic energy before. It is just comes from the contribution of the kinetic energy from the bullet, which is equal to 225 joules. Our system contains 225 joules before the collision. How much our system energy after the collision? Let us compute it here. Kinetic energy after is equal to 1/2 multiplied by the mass, which is 1 kilogram now. And the velocity squared is 1.5 squared. It will be equal to 1.125 joules. You can see the difference between the energy from before and after the collision. We have too much waste energy from 225 to just 1.8. Where does this energy go? It is heat, sound. It has changed the shape of the box here. Stick in that box. If you see here, you will see that you have some black wood because of heat. There's some fire. What we have also, that if we just remove the effect of the air resistance before the collision, we are talking about just the collision. Is that understood? Any questions so far? Online, any questions?
I don't think so.
Yes. Okay. I think we have one more lecture or two lectures in this topic on collisions. We have elastic collisions, and we have some more topics. And then you will see the homeworks. There are no homeworks now. And that's all for today. Any questions? Any questions online? Okay, thank you. I'll end the meeting now.